Want to welcome everybody to this conference. Of course, this being the first session, we may or may not have some technical difficulties, and hopefully Meg's going to be there to bail me out if something happens. Anyways, my name is Ethan Richardson. I'm the Executive Director of SARC here in Saskatoon, not to be confused with SARC with one R. We've got two. We're the oil filter, and antifreeze recycling stewardship program based on an extended producer responsibility model. And we do our part to close the circular economy on automotive fluids and automotive fluid related plastics. Anyways, I'm here to introduce Darren Qualman, who is the author of Civilization Critical: Energy, Food, Nature, and the Future. He is the director of Climate Crisis and Action for the National Farmers Union. And prior to that, he was a project manager with the City of Saskatoon working on water conservation strategies. Darren has been a farmer for probably all of your life, Darren. You can correct me if I'm wrong on that. And for 15 years as a senior staff person at Canada's National Farmers Union, including several years as director of research. He has degrees in biology, history, and political studies. So without further ado, I'd like to pass it over to Darren for his keynote speech.
Thank you very much, Ethan. You can hear me okay?
So far, so good.
Okay, good. And thanks for that great introduction. Really appreciate that. I'm going to bring up my presentation and you can just let me know if that's showing up okay. That.
Perfect.
You're seeing that well and you can hear me okay?
Yep, everything seems to be working good.
Great. Well, I'll just launch right in then. Yes, as Ethan said, my name is Darren Qualman. I'm the Director of Climate Crisis Policy and Action with the National Farmers Union. And my presentation today is on energy and material flows through natural and human systems. And I just want to thank the SWRC and Meg and Joanne and others for giving me this opportunity. I want to thank everybody for taking the time. I hope we're going to have a really good session, and I hope we have some really good questions. So energy and material flows through natural and human systems. I'll just give you a sense of what we're going to cover here in the next 40 minutes or so. The outline of the talk, I'm going to begin by talking about atoms, molecules, and civilizational material flows. Those of you with a chemistry phobia, don't panic. It's mostly just a way of thinking about how materials flow through societies, economies, civilizations. In the second part, I'm going to turn and talk a little bit about energy sources, both in terms of how the material flows are energized and also the energy within those material flows and the materials within the energy flows. And then I'm going to wrap up my talk with a short section just talking about what sustainability is and what sustainability is not. So just to launch right in, atoms, molecules, and civilizational material flows. I'm going to give a number of key insights as I go along, and this is the first one of about 4 or 5. Material flows in 19th, 20th, and 21st century petro-industrial capitalism are linear flows. The flows we see around us right now of materials are linear. And this is wholly and profoundly new. Before about 1850, the material flows in nature and human systems were circular. And I just want to highlight how unprecedented and new this is. The ecosystems on Earth have been functioning for hundreds of millions of years. Human civilizations have been functioning for thousands of years. And for almost that whole time, the biosphere and human systems cycled materials in circles. So you think about the water cycle, the nitrogen cycle, the carbon cycle, the phosphorus cycle, all the critical materials of nature and many of the critical material flows in human systems, they moved in a circle through the system. They came out the other end and then they re-entered the system and moved in a circular flow. But in the last few percent of human civilization, we've created new linear flow systems, and these linear flow systems are both the great strength of our societies and economies, giving us this tremendous consumer goods cornucopia that we see around us, but they're also the great weakness, and they threaten to disrupt and perhaps damage or destroy this civilization if we do not make very, very significant changes. So these linear flows are very, very new. They're very, very powerful, but they are potentially very damaging. So just to help you really fully appreciate what I mean by circular and linear flows and this transition, I'm just going to walk through one example of the transition from from circular to linear flows. And so I'm going to tell the story about agriculture, but it's just one instance of this transition from circular to linear flows. And this transition is much more broadly applicable. It's something that also happened in our industrial production systems and throughout the economy in the making of what we call the modern world. So just to think about agriculture for a moment, we've had agriculture on Earth for about 10,000 years. For 9,900 years, it was characterized by circular flows. So if we think about, of course, the water that grew the crops moved through the water cycle from the clouds to the soil and the plants and back to the clouds, around and around that went. But the fertility also moved in a circle. The nitrogen and phosphorus and other plant nutrients were taken up by the plants, and then when those plants died, much of those nutrients re-entered the soil and then were taken up again by plants. I know if there's some biologists in the audience, they'll say that it's slightly more complicated than that, and that's true. There are some other routes that those nutrients move, but for the most part, nutrients moved locally in a circular flow. In traditional agriculture, the energy supplies within that system were similarly, if not completely circular, at least they were reciprocal. The farmers worked the land, and that land gave energy in the form of food to the farmers, and then the farmers took some of that food energy and brought it back to the land in the form of sowing and weeding and hoeing and harvesting. So the land gave energy to the farmers, and the farmers gave some of that energy back to the land in a circular flow. The same thing with draft animals. The energy supply for the animals that worked the farm was the farm itself. So the grass and the grain and the forage from the farm fed the draft animals, gave them energy, and then those animals took some of that energy and used it back in the fields to grow more grain, etc. So the one way of putting it is the pony worked in the field to raise oats, and then some of that oats was fed to the pony so the pony could go back into the field to raise more oats. These are reciprocal exchanges of energy, circular flows. Even less tangible things like knowledge moved in a circular flow. Knowledge in traditional agricultural systems was largely observational. So the farmers, often women, often collectively, would observe what's happening on the landscape, which plants are thriving, which plants work well together, which animals are producing the best. They would internalize that knowledge and refine their own knowledge about that food system, and then they would externalize it the next year in the form of plans and planting and animal husbandry. So there was this circular flow, information from the landscape to the farmer, and then in the form of plans and actions back onto the landscape, this circular exchange of information. And seeds, of course, moved in a circular flow. The crop produced seed, and then that seed in the next year was used to produce the next crop, and around that would go, and that held for almost 10,000 years. So that's a very brief tour of traditional agriculture, but I hope I've shown you that traditional agriculture was based on a set of circular flows, and that's not surprising, because agriculture emerged from and was wholly dependent upon ecosystems in the biosphere. And of course, ecosystems in the biosphere are completely structured as circular flows. They really have to be. If those ecosystems did not move the critical building blocks of life, carbon, nitrogen, phosphorus, etc., if they didn't move those in circular flows, they'd quickly deplete. Those ecosystems have to run for hundreds of millions of years on a limited quantity of critical feedstocks such as carbon, nitrogen, phosphorus. So the system over time optimized to move those through efficient recycling flows, efficient circular flows, loops. And because agriculture emerged from that, agriculture for the first 99% of the time that we practice it similarly embodied those circular flows. We did something very different in the 20th century and on into the 21st. We replaced those circular flows with linear, or more accurately, humans found ways to crack open the circular flows of traditional agriculture, crack them open, stretch them out, make them linear, and push ever increasing tonnages of fuels and fertilizers and pesticides and other inputs into one end so that we could push ever larger quantities of food out the other end. These linear flow systems are extraordinarily powerful, and they get their productivity largely because of we push ever larger quantities of fuel and energy, etc., and energy-derived inputs into one end and push ever larger quantities of output out the other. So just to talk a little bit about agriculture in particular, so in terms of breaking open those circular flows, moving chronologically, the first circular flow that was broken open was the energy flow. No longer would farms be energized from farm fields. The energy source for agriculture would be distant oil fields. So you set up this linear flow from the oil field to the farm, through the tractor in the field, and then on out the other end into the atmosphere. Similarly, fertility would no longer primarily be something that cycles locally in the fields, etc., or maybe mediated by livestock through manure. Increasingly, fertility would be something that was produced in fertilizer factories or taken from fertilizer mines, trucked in huge quantities, millions of tons, to farms, utilized on the farm, through the field, through the plants, and then on out of the farm in the form of grains that go to cities, and then those nutrients, nitrogen and phosphorus, end up going through the toilet, down the drain, and possibly, if the sewage treatment isn't thorough, down the river and out to deep ocean burial. And a lot of the other nutrients ended up either going off as gas, as greenhouse gas emissions, or making their way into rivers and oceans, causing dead zones, etc. Similarly, seeds, once a circular flow that's largely been cracked open, and now we purchase seeds every year new from seed corporations, and we send them off with our crop and purchase new seeds again the next year. And even knowledge. I talked about how in traditional agriculture, knowledge moved in a circle from the landscape to the farmer, and then from the farmer back to the landscape. Increasingly, knowledge is a linear flow. At one end, you have engineers, geneticists, science, and chemists, and that they produce knowledge. It flows to the farm in the form of custom blended fertilizers, exotic chemistry, herbicides, pesticides, insecticides, advanced genetics, machinery that farmers can't fix themselves, other technologies. So there's this flow of technology and information. So as I said, what the tremendous innovation in the 20th century in agriculture, and this is more broadly applicable, but in agriculture, was to take the circular flows of nature, crack them open, stretch them out, make them linear, begin shoving millions of tons of petro-industrial inputs into one end, and thereby forcing ever increasing quantities of food out the other end. And this was done not just in agriculture, but throughout the entire sort of 20th century civilization and economies. So that's key insight number one. I'm going to give you another one here. Key insight number two. Atoms are indestructible. The carbon, nitrogen, phosphorus, other atoms that we move through our economy, they're not destroyed in our economy. They could be, I guess, in the hearts of stars, but for the most part, in ecosystems and economies, atoms can be treated as indestructible. Many molecules persist, they don't break down, and everything ends up somewhere. So the insight is whatever we push into one end of our linear petro-industrial systems comes out the other end. So if we take those two insights and put them together, we come to something that many of you have maybe thought of, and that is if we push billions of tons of indestructible atoms and persistent molecules into one end of our linear systems, they will come out the other end. So if we put those together, we come to a third insight, and I think this is really the pivot for my talk. This is really the key, because I hope to give people sort of a foundational understanding of how things fit together. And I would suggest to you that our civilization's linear flow structure is at the root of nearly all of our ecological crises. That linear flow structure is the cause of climate change, ocean dead zones, dying reefs, accumulating toxicity, oceans full of plastics, deforestation, other depletion and pollution, and even to a very significant extent, habitat and biodiversity loss and extinction. So let me just walk you through some of the background information that has led me to that conclusion. As I said, atoms are indestructible, so we're going to take a quick look here at how those atoms move through the economy: carbon, nitrogen, phosphorus. We're going to talk a little bit about plastics. So all the atoms we push into our linear production system come out the other end. That's just a truism. They're indestructible. Everything has to go somewhere. So every atom we push into one end comes out the other end. So, for example, carbon atoms in fossil fuels go in, and carbon atoms as carbon dioxide come out. And this leads to several effects, including climate change and ocean acidification. Just talking about climate change, this is a graph I produced of carbon dioxide concentrations in the atmosphere. It covers 800,000 years and up to the present. And the units are parts per million, but don't worry too much about units. Just kind of look at the general shape of this graph. So you can see that over the last 800,000 years, carbon dioxide concentrations in the atmosphere went up and they went down. The low points in that graph actually correspond to what we call ice ages. There's about 10 of them on view there. And I should say that the 800,000 years that we're looking at here, just to put that in perspective, that's about 4 times as long as modern form humans have existed on Earth. So it's a very, very long time. So carbon dioxide levels in the atmosphere went up, they went down, but note that not once did they go above 300 parts per million. Now they're at 417. So the greenhouse gas concentrations in the atmosphere right now are unprecedented in the last 800,000 to 1 million years. The other thing is how fast they're rising. So if you look, I think you can maybe see my cursor there. If you look at the low point just before the modern period, between there and 1900, that's a rise of about 100 parts per million. That took 10,000 years. But the rise from 1900 to current, again, about 100 parts per million, that took 100 years. So the previous increase took 10,000. This time it just took 100. That's 100 times faster. And that correlates with what scientists are saying. We are driving up CO2 concentrations in the atmosphere 100 to 1,000 times faster than any time in the geological record. So what are we really seeing here? Well, what we're seeing is this, that since the beginning of the fossil fuel age, we've pushed into our energy and economic systems 500 billion tons of carbon atoms. 500 billion tons of carbon atoms in the form of coal, oil, and natural gas. And all those carbon atoms came out the other end of our linear systems. That 500 billion tons of carbon atoms have now accumulated in the atmosphere. That's what this graph shows, and also in the oceans. So looking at carbon atoms again, but in a different form, everything we push in comes out. Carbon atoms go in as fossil fuels and other sources, and they come out as methane, CH4, methane. This leads also to climate change. This is a graph of methane emissions in the atmosphere. It's a little different time scale. It's 10,000 years. You can see that methane concentrations in the atmosphere over the last 100 to 200 years have doubled. They were fairly stable for about 9,800 years. And then in the last century or two, they've doubled. And this is quite consequential. As some of you will know, methane is a greenhouse gas about 28 times more powerful than CO2 when it comes to causing warming. Moving on from methane to and carbon to nitrogen. Nitrogen, another atom that we're pushing into our systems in very large quantities. Nitrogen atoms in the form of fertilizers, that goes in, and nitrous oxide and other nitrogen compounds come out, and that leads to several negative effects, climate change, ocean dead zones, damage to terrestrial ecosystems. Nitrous oxide is a greenhouse gas that's 265 times as powerful as CO2, a very powerful and long-lived greenhouse gas. It's really stunning what we've done in terms of nitrogen. Many of you will know it's one of the key plant nutrients, the heaviest applied fertilizer. It's often the limiting factor in plant growth. We humans have tripled the amount of nitrogen cycling through terrestrial ecosystems. And I'll just explain that a little more. If you think about the land-based ecosystems, the forests, the farmland, the wetlands, the grasslands, rainforests, savannas, tundras, etc., all of those ecosystems on land. If you think about the amount of nitrogen that was cycling through those before the Industrial Revolution, it's now 3 times higher as a result of human interventions, largely fertilizer. This next slide is the cover of an article from 2009 in the peer-reviewed science journal Nature. It's written by Johan Rockström and Will Steffen, and it talks about the safe operating space for humanity, and it talks about planetary boundaries. And I'll just zoom in on that figure on the front. This is a graph. The green circle shows that the safe operating space for humanity, for planet Earth, and then the boundaries. And those red lines radiating from the center show how far we've pushed human interventions. The one in the lower left isn't surprising, biodiversity loss. Humans have triggered the fastest extinction event in 65 million years, the fastest since the destruction of the dinosaurs. But most people wouldn't be able to name the other planetary intervention where we've pushed farthest past the planetary boundaries beyond the safe operating space for planet Earth, and that is nitrogen. We've got a tremendous nitrogen problem. As a matter of fact, I would suggest that if we didn't have a climate crisis, we would all be talking about the nitrogen crisis. And again, this is the result of pushing trillion or billions or trillions of tons of nitrogen atoms into linear systems, and in this case, mostly agricultural systems. A little closer to home, little more recent. This is a graph of nitrogen fertilizer use on Saskatchewan farms, and it covers the last 50 years, 1968 to 2018. Farmers in Saskatchewan have doubled the tonnage of nitrogen fertilizer they're applying just since 2007, and they've quadrupled the tonnage since 1991. And you can see the graph is still trending very strongly upward. So it looks like we're on track to double and redouble nitrogen use again. Just to look at what that means to emissions, this is agricultural emissions in Saskatchewan. complicated graph, but there's just 2 points I want to point out here. The top line's going up. Agricultural emissions are going up. They're up by about 50% just in the last quarter century. And what's driving that? Well, those two blue sections at the bottom, the light blue and the dark blue, those are emissions from the production of nitrogen fertilizer and the use of nitrogen fertilizer. And you can see it's that upward trending blue area at the bottom that's really driving the increase at the top. So moving on from individual atoms to molecules, I'll just give you one example of that. Many of the molecules we push in come out the other end. They persist, they don't break down. Plastics go in, plastic molecules go in, and plastics and microplastic fragments come out the other end, and we end up with oceans and wildlife full of plastic and human food and water full of plastic. This is a graph I put together of plastic production over the past century, 1919 to 2019. And you can see the very, very rapid increase, the exponential increase.
Darren?
Yes.
So I'm just going to interrupt you. It seems we've lost your presentation.
Well, thanks for interrupting and letting me know.
Yeah.
Looks the same on my end.
Maybe just unshare and share it again.
Okay, share and share alike. Okay, I think, have I unshared? I'll try and reshare now. Are you seeing my screen now?
Yes.
Okay.
In your full screen though, so just head to your presentation. Yeah.
Okay. Do you see a plastics graph?
Yep, I do.
Excellent. Thanks for interrupting. I don't know what happened. It wasn't touch anything. Okay. Thank you. Thanks to the tech people. That's great. So plastics production over the last 100 years, it's doubled and redoubled, and that trend line is very, very sharply upward. And I don't have it here today, but I could show you projections from the plastics industry of it continuing upward and upward and upward and just doubling and redoubling. So I've shown you some various materials that are moving into our system and through those linear systems and out the other end. So let's just look more generally at materials as a whole. This is a graph of the billions of tons of material that move into our economy and civilization every year. It looks a little messy because it's made from 7 or 8 different data sets, all of which are from peer-reviewed journal articles or from UN sources. It covers about 250 years, 1850, and then it projects out all the way to 2100. This is a graph of every material that moves into our civilization. So it's fossil fuels, wood, plastic, grain, steel, concrete, aluminum, sand, diamonds, gold, everything except water. Water is excluded from this. But this is a picture of how much material we're moving in to and through our productive systems. So I'll just give you a sense where we are now. That red oval shows you where we are now, and then it projects where we're going to go over the next 80 years. We're at about 90 billion tons per year and increasing. So we think about the next decade, we're at about 90 billion now. It'll go up quite a bit over the next decade. So for ease of math, let's just think about 100 billion tons per year. Well, over the next 10 years, that means we're going to push 1 trillion tons of material into the system. And because these are linear systems, we're going to push that in and it's going to come out the other end. So the thing we need to understand if we're sort of being realistic about sustainability and what we're up to in economic growth is that governments, corporations, citizens, etc., think that what we should do over the next 10 years is extract and mine and produce and pump 1 trillion tons of material, put it into one end of our linear food systems and production systems and other systems, knowing full well that most of that 1 trillion tons is going to come out the other end and end up somewhere, probably in our atmosphere or our landfills or in our oceans. So I've talked a lot about materials. I want to talk a little bit about energy sources. So as many of you will know, until the 18th century, all energy systems on Earth relied on solar power. And then we did something in the 19th and 20th century. We made a transition to non-solar sources of energy. And the result was accumulating CO2 in the atmosphere. I showed you this graph a moment ago. But let's think deeply about what this graph tells us. What's really happening here? The underlying problem is that most of our modern energy sources have material carriers. Material carriers. It's not just the energy in fossil fuels that causes the problem. It's the materials that carry that energy, carbon atoms. So fossil fuel energy creates a carbon dioxide problem, and that really is a problem with the accumulation of material, in this case carbon. So we're not just extracting and producing and distributing energy, we're extracting and releasing billions of tons of materials, and the problem really is spent fuel. The climate change problem really is a problem of spent fuel emerging from the end of linear material flows, in this case in the energy system. And I just want to generalize a little bit, and that is all energy sources that come with a material carrier will cause problems. Now, why is it important to know something like that? Why is it important to think about the fact that all energy sources that come with a material carrier will cause problems? Well, because we're on the eve of an energy transition, and all of us as democratic citizens need to think about what kinds of energy sources we should have in our civilization. We need to make some choices about how we're going to power things moving forward. So we've got a number of choices. Some of those energy sources come with a material carrier, some don't. So the ones with a material carrier, oil, coal, natural gas, have a carbon carrier. Nuclear uses uranium, biomass, again, carbon. And then there's several energy sources without a material carrier: solar, wind, and hydro. I would suggest that the ones on the left probably aren't good candidates for powering our society. I think most of us understand why the fossil fuels aren't. I could say a little bit about nuclear, and I don't want to get sidetracked into a big argument about nuclear power, but it's topical right now because the Saskatchewan government is talking about small modular nuclear reactors. Some people would say that we can do that safely, that we can safely mine, process, utilize, and then dispose of uranium. I would suggest that the data show something different. If we can imperil the biosphere with carbon, we can probably imperil the biosphere with uranium. If we can damage ecosystems with plastic, we can probably damage ecosystems with uranium. And a more general way of saying that is this, and this is key insight number 4. Virtually every material we have mobilized in massive quantities, be it carbon, nitrogen, phosphorus, plastic, wood, water, etc., is now causing huge environmental problems, either in terms of depletion or pollution. That's not surprising. We're pushing these materials through linear flow systems. You've got a big mine or a well at one end. You've got this productive system in the middle, and then you've got these ejectors out the other end. So if you're going to utilize these materials in large quantities, you're going to deplete them at the input end, and you're going to have a massive accumulation causing all sorts of ecological problems at the other end. So this tells us a lot about how we should structure our civilization moving forward. For materials, of course, we need circular flows. For energy, we need sources that don't have material carriers, which means solar, wind, and to a limited extent, hydroelectricity. So that's a little bit about energy and how energy and materials relate, and how we need circular flows of materials and energy that doesn't come with a material carrier. I'm just going to wrap up my talk here in a couple of minutes just to talk about what sustainability is and what sustainability is not. And I'm going to give you a bit of a provocation, perhaps. I mean that in the sense that I want to provoke some questions, some thinking, and maybe a little debate. And here's my provocation. The definition of sustainability is not ambiguous. The word sustainability has exactly, precisely, and only one definition. It's very, very simple. It's not debatable. And the definition of sustainability is this: sustainability equals circular plus solar. And that isn't some idiosyncratic definition that I cobbled together. It's simply the reality of what happened on planet Earth for hundreds of millions of years. The reason that biological systems could not just continue but thrive and grow and generate diversity and beauty and stability for hundreds of millions of years is they moved materials in circles, and the whole thing was powered by solar energy. And human systems for thousands of years did the same thing. We moved most of the materials in circles, and the whole thing was powered by solar energy. This is the only definition of sustainability. If people are moving rapidly and aggressively toward circular flows and solar power, they're actually pursuing sustainability. If they're doing other things, they're not. So, yeah. So, if we do move to circular flows and solar energy, we're going to end up with systems that we avoid the drawdown, we avoid the accumulation on the other end. And we may actually be able to repattern and restructure this civilization so that it can continue through this century and possibly the millennium. So that I would suggest is the one and only credible definition of sustainability. I just want to get at this a little bit, though, from another angle. I just want to talk about what sustainability is not. And I want to do that by just asking you to just picture sustainability. You can close your eyes if you like, but you needn't do that. But just in your mind's eye, just kind of think about and picture sustainability. And when I do that, certain things come to mind, things like stability, the system isn't in crisis, constancy, it's not growing dramatically, it's not collapsing, horizontal trend lines, we're not using twice as much and then twice as much again of things. We're not seeing species collapsing. The trend lines are more or less horizontal. Everything is stable and I would say sustainable. So that's, when we think about sustainability, that's what we picture. But here is a picture of the civilization we actually find ourselves in. This is a graph of the last 2019 years of economic activity on planet Earth. Global gross domestic product, or what they call gross world product. And you can see that for the first approximately 9,800 and some years, things were relatively stable, and then things just took off almost vertically. There's no horizontal trend lines here. This doesn't look very sustainable. And the question I always have when I sort of graph this data and see just what's happening is I just wonder, why is no one talking about this? But I realize that they sort of are. And this is a headline from CBC from a year or so ago. Just one selected at random. It says, Canadian economy grew at 2.9% pace in second quarter, lower than expected. So the economy is growing at just under 3% per year. Some of you might know a quick little trick to figure out how fast something will double. It's called the rule of 70. So you take 70, you divide it by the growth rate, if you've got a constant growth rate, and that tells you how long it'll take a system to double in size. So if the Canadian economy is growing at about 3%, 70 divided by 3 is 23.5. So at this growth rate, about every 23.5 years, the economy will double in size. So let's say 25 years for easy math. So 25 years from now, it'll be twice as big. 50 years from now, it'll be 4 times as big. 75 years from now, it'll be 8 times as big. And 100 years from now, it'll be 16 times as big. When you see a headline talking about 2.5%, 3.5% growth rate, what you should say to yourself is, holy cow, we plan to make this economy 16 times larger over the next 100 years. And what if every economy on Earth is trying to do that? And of course they are. Growth is sort of the prime directive in neoliberal economies. What does it say about sustainability if we're going to make our economies 16 times larger? And it's not just the economic size. This is that graph again showing the trillions of dollars that we're moving through the economy. But here's the energy use graph. I hope you can see there's a set of tan diamond-shaped points there that show how energy use is perfectly tracking the very rapid exponential increase in economic activity. Not surprisingly, here is the emissions, and those red diamonds there, that is material use. This is the same data I showed you a moment ago when I was talking about 1 trillion tons over 10 years. It's just graphed over a different time scale. Instead of 250 years, it's graphed over 2,000 years. So you can see how rapidly that's going up. Sometimes when I go to conferences, people talk about dematerialization as if somehow the economy is growing and material use isn't. I think that graph should really call into question ideas about dematerialization. I'm just going to skip over these slides on energy, and I'm just going to conclude by saying what we have to do is very, very clear. The definition of sustainability isn't ambiguous. There's just one definition. It's simple, and that is sustainability equals circular plus solar. And I think people in this conference are going to be talking a lot about circular flows of materials. And I would say that we're all part of a quest to find sustainability, and that to really sustain this civilization for centuries to come, we must install those circular flow material systems. They must be powered by solar energy. And to do anything else is to pursue something other than sustainability. So that concludes my talk. Thank you very much for your attention. Thank you for the luxury of having a good long time to speak. I usually make shorter presentations, but it's nice to be able to connect a lot of dots. I hope I've told you some things that are new and interesting. I have a website, darrenqualman.com. A lot of the graphs that you saw today are on that. I'm working at the National Farmers Union, and I'm the Director of Climate Crisis Policy and Action. And about a year ago, I put out a book called Civilization Critical: Energy, Food, Nature, and the Future. And it goes into depth on a lot of the ideas I've talked about today. It's available from Turning the Tide booksellers in Saskatoon, and you can order it from any independent bookstore or from the online seller of your choice. So that concludes my talk. I'll try to unshare my screen, and I look forward to questions.
Here we go. Okay, great. Thank you very much, Darren. Of course, we're all giving you a virtual round of applause for your presentation. You may not be able to hear it over the audio, but I'm sure we are all clapping. So yeah, thank you very much for that thought-provoking and quite decisive view on circularity and linear material flows. We have one question from the audience asking a little bit about how population growth fits into these energy and material use patterns. And of course, there's also a little bit of a discussion online or on the chat room about how those population growth does in fact follow the energy and material use. Can you comment a little bit about about that aspect of population versus those kind of exponential patterns we're seeing?
Sure. First, just a caveat and disclaimer. I'm always hesitant to talk about population because I know here we're having a good faith argument or discussion, but sometimes people in bad faith try to sort of shift the discussion away from the impact we're having in places like Canada to other parts of the world where populations are larger. But I don't sense that's where the question comes from. Population is an interesting variable here in that it's both cause and effect. There's a reason that populations on Earth were very, very low for a long time, and that with the advent of fossil fuels and more specifically nitrogen fertilizer, populations have taken off. So populations have grown because of the changes we've made in our systems, and then population increase has in turn driven things as well. If there was fewer people, there would be perhaps less production, etc. But as many of you know that work on environmental issues, total impact equals number plus individual impact. So the number is going up, but we also have to look at the impact that those of us, especially in advanced economies, are having.
Okay, great. Thank you very much. I think if I can sum up, population is one of those variables, but it's certainly not a catch-all answer for our environmental situation, right? So thanks for that.
A billion people living like me can wreck the planet.
Right. So secondly, I've got a question from Christina. Do you consider wind energy and solar energy to be equivalent in terms of the sustainability equation?
Yeah, that's a good question. No energy source is perfect. Wind energy, wind turbines can kill birds. Solar panels require a lot of materials to make. We probably shouldn't try and deploy wind and solar on a scale that it would take to run the current system and then double it and redouble it again. But at this point, in order to make things work, again, keeping in mind that there is going to be some negatives to all of these, we probably need to deploy wind and solar in very large quantities. Industrial scale wind probably, and then more distributed on-site solar. I've got solar panels on my property here, but it's a good question and one that I can't wholly answer in terms of what the relative costs and benefits are of the two power sources.
Okay, thank you. And of course, if you have follow-up questions to the questions that are being asked, please feel free to type them in, and maybe we'll circle back towards those follow-up questions later, or raise your hand if you want to ask them yourself, of course. And then I'm just going to skip over Henry's population growth and industrial. Oh, I'm going to actually, this circles back to the first question, right? So population growth and industrialization, of course, are putting pressures on our natural resources. Any thoughts about how to slow down these pressures?
Yeah, one way we can do this, I mean, we have tremendously productive systems right now. And one thing that we can try and do to slow down the pressures on natural resources is to encourage people and put together a set of incentives so that people take more of that productivity and that wealth creation in the form of free time and leisure and time with other people rather than the form of material goods. It's just not going to work if we continue to work 40 hours a week, take home very high salaries, and then try and convert those salaries into cars and jet vacations and houses full of stuff. We need to say to ourselves, this industrial system is very, very productive. So I can either work as much as I do now and consume as much as I do now, or I can work less and consume less. And we really need to take some of the wealth and productivity of our civilization in the form of free time and time with friends over coffee or wine. I often tell people that France in the 1960s, they managed to create this incredibly lush society with poetry and romance and philosophy and good books and a lot of time over wine and in cafes, etc. And they did so probably with about a tenth the fossil fuel consumption that I'm burning here.
Yeah, interesting perspective on that for sure. And I completely agree that slowing things down personally will lead to a slowdown nationally and hopefully lead to less resources. Another comment from Peter here about the historical circular economy. And I'm reading into what Peter's typed in here. So hopefully, if I'm off base, Peter, please jump back in or raise your hand. But his comment is that there have been linear systems in place kind of since humanity stopped being nomadic, and whether or not that has to do with trade routes or movement of goods from one place to another, or places of excess to places of scarcity. He's saying that there are some linear systems in place there. And then he comments with, of course, we do need to find a way to close the loop. And I'm just wondering if you can comment a little bit more about that historic context.
Mm-hmm. Yeah, in researching my book, I spent a lot of time looking at the history of how materials flowed. And there really was, because materials were very, very hard to get. Like if you think of something like cotton cloth, the cotton had to be grown and then hand picked and hand carded and all this. Before industrial spinning and weaving, that cloth was so hard to get, or woolen cloth, that it was reused. It was conserved, and even at the end of its life, it was taken apart. Cotton cloth became paper, and wool cloth was often taken apart and then rewoven. It was called the shoddy trade. There was rag pickers. Even there's a great story about how all of the dust and garbage and detritus and fireplace ashes of London were carted to a central location and carefully sifted. And all of that dust and fireplace ash was reused to make everything from bricks to fertilizer. So, yeah, there was a lot of circular flow in traditional economies. And the other thing was that they just couldn't really have very good linear systems because they didn't have the fossil fuels to power them. You couldn't have huge mines at one end because mining was incredibly labor intensive. So they were sort of circular by, they were forced to be so. But all of that said, I think Peter makes a good point that there's always a long tail to this, that there's always some linear flows. Somebody's always taking gold out of a mountain somewhere and bringing it across the ocean. But that said, if you think about the average person, the food systems, the clothing systems, the heating systems, the housing systems they have, most of that was a circular flow system. Things were very local in space. The transportation over long distances was just very hard. So the point's well taken that there was some linear flow, but most of what people touched was circulating fairly locally.
Great, thanks for that. And of course, Meg, you can jump in if we're running out of time. I think we are approaching 12. And I think we can go a little bit longer. And of course, the conversation can continue in one of the chat rooms. But next question from Rod Johnson. He believes you're describing a steady state or a non-growth economy. And I know you mentioned that current philosophy is that, we need growth. We need growth at all times, and 3% is not enough. So of course we're going to need to rethink on how that growth has to occur. So he was just wondering if you had any thoughts on how that might look like, or how it might be achieved. And you touched on a little bit on this with the personal use, but if there's anything else you want to expand on.
Yeah, it's a difficult problem in terms of how you slow growth and stop it, and then even begin to make the economy a bit smaller in a controlled way. Because one of the real changes in the mechanics of the structure of civilization over the last couple hundred years is we went from systems that were governed by negative feedback. That's like your thermostat. When things started to ramp up in the economy, it ran into various limits like land area and food shortages, and then the economy would sort of cool down. And for hundreds of years, there'd be this sort of speed up, slow down, speed up, because the whole economy was under a negative feedback loop. What we did very recently is we rewired it and turned that around, and we made a positive feedback system. And that's what's caused the explosive growth. If you recall that graph I showed you where things are about flat for the better part of 2,000 years and they go straight up, what you're seeing there is the replacement of negative feedbacks with positive feedbacks. Now, growth begets growth. If the economy starts to heat up, more people are employed, they have more money, they spend it, and the economy heats up more. So you've got more begets more. So we've got a positive feedback system, and that makes it hard to move to an economy that's not growing or that's contracting, because positive feedback not only drives the system upward very fast, but it can drive it downward very fast. So that it starts to contract, people get laid off, spending falls, then it contracts faster. And we had a taste of that within COVID here, and that's why the massive government interventions were needed. So we not only need to think about a steady state or a slowly contracting economy, we need to think about how to rewire the connections in that economy such that if this thing stops growing, it doesn't immediately go into its other default mode, which is very, very rapid contraction.
Great, thanks for that. One more question here. I think we've got time. It relates to how the linear circular flow systems can impact municipalities, and I'm guessing we're looking at individual administrators and communities. Do you have any comment how municipalities might be able to take advantage of this system or change things in their own backyard, so to speak, to help out with this problem?
I think municipalities are doing a very good job in trying to initiate circular flows, recycling systems, etc. I think though that we have to move this problem up the line quite a bit. That graph we saw, for instance, of plastics, if you just continually double and redouble the amount of plastic being produced on Earth, it's a bit much to ask municipalities to constantly scale up to recycle more and more of that, and we know that recycling is often very difficult. We need to change the whole structure of our production and recycling systems such that things are made to be recycled. But another thing that's worth thinking about is how our systems differ from natural systems. In nature, the production and decomposition is in perfect balance. Composition and decomposition is perfectly balanced. In our petro-capitalist economy, we spend $10 or $100 on production for every dollar we spend on recycling. There's just a real imbalance there. And I think throughout the economy, we need to engineer in at the front end more sustainability and more recycling, but we also need to really ramp up the efforts to better balance production with decomposition and recycling.
Great. Yeah, we just, I may have said the wrong name there for that last question, but that last question was from Augustina Osaseri, I believe. I've just got one quick question. If nothing else shows up, then maybe we'll wrap it up afterwards. But you did mention something about incentives and incentivizing behavior in your presentation, and that's something that's near and dear to my heart as an organization who does provide incentives for behavior. Is it your contention that some of these inputs might be priced inappropriately based on their scarcity, or is it your opinion that the outputs are priced inappropriately, right? Because if we look at nitrogen use in Saskatchewan, maybe there's an optimal nitrogen application that again internalizes those inputs, where you're putting a little bit of nitrogen in, but you're actually just producing and putting enough in to optimize plant growth, or to have good plant growth. But if you double it, maybe you get a 5% increase in growth, but then you end up with all of this runoff. So from an economic perspective, it might be worth it to put twice as much nitrogen in to get that extra 5%. So what are your thoughts on how to kind of balance these economic factors to encourage people to be reasonable on their use of these inputs? Hopefully that question makes sense.
It sure does. Yeah, thanks for that, Ethan. Yeah, it's often the problem what people call externalities. We pay for we literally get gasoline in our tanks for the price of pumping it out of the ground and refining it, and a little bit of taxation. And none of those other factors, destruction of coral reefs, ocean acidification, none of that is factored in. All of those externalities are left to nature. Coal-fired power plants spew a lot of carbon particulate, and that causes a lot of lung disease and death. None of that's factored into the price of electricity. So there's a lot of unpriced externalities. So we need disincentives, picking up on your terminology, we need some disincentives to stop our demand from doubling and redoubling, whether it be nitrogen or gasoline or plastic. But there's another piece when it comes to incentives. I'm often puzzled as to why certain types of recycling are difficult. For instance, I don't know what the recycling rates for an aluminum can is, for instance, but you could easily make it 99 point something percent. You just you just decide what percentage of these materials you want returned, and just tell the public, we're just going to keep increasing the deposit until that percentage comes back. And if 20 cents on an aluminum can doesn't get you 99.5% back, maybe 30 cents or 40 cents does. There's a lot of very small tweaks we can make to the system that will begin to close some of these loops.
Great. Yeah, thanks again for your presentation and your question and answers. I'll give one last call for any additional questions before I turn it back over to Meg to wrap it up. I guess I'm going to count down from 10 in my head, maybe. And if nothing else shows up, then we'll shut it down.
Yeah, sounds good.
Yeah. Again, yeah, just want to extend our thanks, Darren. There's been lots of positive feedback on the chat room there. I'm sure you can see it as well. Great presentation, and thanks for your time.
Thank you very much. Really appreciate it.